You are listening to EE Times On Air, and this is EE Times Current. I'm Eric Singer. Today's episode was produced with support from Siemens EDA, and we're going to have two guests today from the Siemens Calibre team. Sheva Nolke is a principal product manager at Siemens EDA, bringing 24 years of semiconductor innovation to her leadership in the Calibre 3D IC physical verification team, where she pioneers solutions for 3D IC analysis. Drawing from her unique background as a former photomask fab line engineer, she spent the last 10 years driving technical breakthroughs in the Calibre division. Known for her innovative problem-solving approach and talent for building collaborative teams, Sheva has become a driving force in advancing holistic solutions for the chip design community. Also joining us is John Ferguson. He's the Senior Technical Director for Calibre Physical Verification, managing product vision and direction across all physical verification offerings from Siemens EDA, including design rule checking and related shift-left solutions. With over 27 years of EDA domain experience, he brings a wealth of knowledge and history to modern challenges such as 3D IC, photonics, quantum compute, and much more. John and Sheva, thank you so much for joining us today.
Thank you for having us.
Thanks for having us.
We're in the midst of this evolution right now, dare I say revolution, as we go from traditional 2D SoCs or even 2.5D chips on interposer, as we move into the era of true 3D stacking. What new challenges are you all seeing arise? And John, I'd love to start with you.
Yeah, I think there's a lot, right? I mean, for several decades, we had a pretty well-defined 2D process. We knew that if you follow the PDKs correctly, generally you're going to be safe and everything's going to work as expected. That's now starting to change when we go to 3D, and that changes for several reasons. We really kind of got an explosion across several dimensions. There's new materials that weren't traditionally, not something we cared about on the traditional single level SoC. Of course, now we're also introducing heterogeneous processes. That's a big challenge. Mm-hmm. Now we're stacking in a third dimension. That adds a whole bunch of new things there. On top of that, there's just the huge extent of extra data that we're now processing because we have all of this extra stuff, right? So you've got a lot more that you have to consider. Think about, for example, the huge AI chips that are being designed today. Traditional EDA tools, you just can't handle it. You can't really do them in a 2D space. They don't have enough capability, right? You go beyond the reticle limit. So you have to go into some form of a 2.5D or 3D format, and it's just tons and tons of data and extra stuff that you have to check on it. So there's new approaches that are required to meet the reasonable design cycle times. Beyond that, we also have things like thermal impacts. Thermal impacts really make things trickier because, on a 2D space, these are pretty easy to dissipate. Your heat is basically right at the silicon level. Silicon will take that heat and move it out pretty easily. So, now that if you're confined to that single homogeneous chip, that is all fine and good, but now we have all of this stacking going on. We have all these different materials. They're going to behave very differently once you start pushing the power through and heating everything up. You have to be very careful.
Yeah, the size of the components growing and the number of components growing is part of the challenge, but there's also an expanded need for tighter collaboration all around. So this could include between EDA providers and foundry. This could include package designers collaborating with chip designers, foundries with OSATs. Ultimately, what we need to focus on is creating these usable flows that address the real risks of failure. And that requires common languages, cross-functional teams, and the highest level of collaboration. In addition to that, there are critical technologies and IP that need to be protected in this conversation. So foundry process and technology and around how OSAT processes work. This protection of IP is going to make necessary these sort of common languages, even in the context of all this interoperability. So as a vendor to these customers, we really think about how can we make it a tighter integration among all of those teams.
Absolutely.
I guess one more challenge that we think about is considering the design closure time. So the complexity being higher and higher, these design starts are going to have to start earlier and earlier and really shift some of these multiphysics considerations at the beginning of the design cycle rather than closer to the end.
Shift left is certainly a philosophy we have spent a lot of time talking about, particularly in the last year or so, and in the context of these complex 3D chips, of course, AI chips, that's only becoming more and more relevant. So given all of these challenges, how do companies successfully work across these design barriers and personas and get in alignment?
Right. As I mentioned, the integration across teams is going to have to be tighter. With multiphysics, it will be a matter of bringing the expertise of the mechanical, thermal, power, and timing experts into the hands of the package and die designers. So the codification of the multiphysics analyses into flows that are accessible earlier, as we mentioned in the design process, it increases the degrees of freedom for revisiting how and where things are placed, and that'll avoid the late stage issues from the multiphysics domain. And as I mentioned, again, a consistent set of common language is going to be critical for describing this type of technology across teams. 3D blocks is a good example of how to unify this type of communication. And then with the more complex packages, some, as John was mentioning earlier, previously held assumptions are no longer true. So, for instance, multiphysics analyses historically would assume a die-level description that could be represented using a uniform cuboid. And after careful research and studies, we're seeing that mechanical, thermal, and power influences can actually have enough impact to interrupt the expected die-level behavior. So that will require that we include our die-level designers in the conversation around multiphysics criteria.
This kind of challenge also means we are being driven more and more towards integrated cross-tool flows and ultimately towards more standards across the industry. So as an example, if we think about thermal analysis, and Shweta already alluded to this a little bit, but in order to get accurate calculation and contribution of all the elements in your 3D IC, that really should be including things like the GDS2 level elements, your wires, your oxides, your transistors, that whole 9 yards. That's something that has been left out historically. And so now if we're going to pull that in, how do you go about doing that? On the Calibre side, the way we've implemented this in our 3D thermal solution is through a built-in integration that combines Calibre. I think most people that are familiar with Calibre know it's really the top tool for accurately reading and understanding what's at the GDS level, understanding all the layers, their shapes, how they're connected, etc. We integrate that with the SimCenter FlowTherm solutions from Siemens as well. FlowTherm itself is also an industry-leading standard in the industry for its ability to do the thermal analysis. Like Shweta was saying, traditional FlowTherm will go down to the chip and will look at the chip as a homogeneous brick, if you will. So Calibre can bring in that detailed level information. We take that and we create a model, essentially a thermal model that FlowTherm can read. So under the hood, we pass that to FlowTherm, a built-in version of FlowTherm. It then does the simulation and does what it does, right? It's very accurate and very well known. When we get that information back out, Calibre transforms it into a way that is suitable for a typical IC designer, right? They can understand it, visualize it, using the same tools that they've always used with the integrations, not just to the Siemens tools, but to other design tools that they might have in their platform. This is kind of how we're looking at some of the personas and the like in order to bring things to the market easier. So, for example, somebody that is designing a 3D chip, maybe they've come from a 2D space, they know how they've done it historically, but now you have to add these extra elements in there in terms of thermal, potentially even in terms of mechanical stresses. They don't have to be a thermal expert to get there, right? We can push button, essentially show them, here's what your impacts are, and then they can make educated decisions on how to improve upon that if needed. So that's really what our emphasis has been. We also want to emphasize automating it as much as possible so that they don't have to understand the historic ways that a thermal expert, for example, would go into details and understand at a higher level what all of these things mean. It's really setting it towards individual personas so that we can help them do their job faster without them having to ramp up so much historic learning, if you will.
The degree of complexity here is fairly staggering. And so can we still safely ensure timing closure?
I'd say the good news is we can do it. The bad news is it's much more work than it used to be. Right. So for timing closure, for example, we need to understand the power and the thermal and the stress impacts all essentially at the same time, right? Power will generate heat. Power will run fast. The power gets to your devices quickly, but it takes a little bit of time for that heat to generate. That heat can then also impact the mechanical stresses because the materials are expanding and contracting at different rates. That happens much more slowly. So we have to kind of iterate these things through to come to a steady state, to understand what is the real impact as all of this is kind of matured. You can't just start from, I have my estimated power and that's all I need to know, right? Your power, ultimately, what you wanted the power to be is not the same as what your power is going to be after it's been heated up. So that's part of what we have to address through this. If we think about chiplets in the context of a 3D package, those also may not behave the same on the test bench as they do in the package, right? For the very same reasons, right? So this kind of idea of known good die starts to break a little bit because, I can get a chip or a piece of IP that I want to put in as a chiplet into my 3D IC. I can test it on the bench. It's going to meet my timing as I expect. Now I put it in the context of a larger assembly with other chips, some of them getting hotter, temperatures are changing, the stresses are changing. What does that do to the electrical impacts that you're going to get on the other side of this? In some cases, it can knock you out of the margins that you had set. So you have to be careful, in other words, right? What else can I say? Beyond that, I would say, there are things that people do, some best practices. You'll hear people talk about not just doing known good die, but if you're going to have a stack of different dies on top of each other, then doing known good stacks, and even thinking about putting those stacks on a substrate or on an interposer, right? So you have to check and check and check. And of course, the higher up you go, the scarier it becomes, right? Because it only takes one chip to fail for your whole 3D IC to fail. So you really have to be careful. And that really comes back to what Shadla mentioned earlier about doing your analysis early and often in a kind of shift left approach.
In collaboration with our customers, with our Calibre 3D stress tool, we've already been able to demonstrate how the post-packaging behavior of the die can be different as the test bench behavior. So you can clearly see that integrating this component, this die or chiplet, into the package will affect some kind of stress impact on the die itself. And what we can see from that is this residual stress after that process could potentially put their circuits outside of the expected behavior. And so what we're enabling our customers to do is to model and understand how those circuits may be impacted. And then that allows these designers to then go and check each new design and see, not necessarily quantitatively, but qualitatively, if I assume this device behavior across any location, where am I in good shape and where am I not in good shape? And doing this early on, again, gives the designer more degrees of freedom, so they can choose better where to place specific sensitive devices and avoid the high stress regions that might affect the circuit behavior.
John, how do you see this all impacting the overall design tool chain?
Unfortunately, it also gets larger, right? So it means more tools that users have to buy, more effort that's going to be required. If you think about it, I mean, we're bringing in chiplets into a larger system. That means you still have to do your standard 2D verifications and everything else, right? You got to do the place and route. You got to do your timing and your simulations, your verifications, everything that you need to tape out the specific chiplets individually. Mm-hmm. But now you have to go beyond that and pull in all the data across the assembly to understand how is that going to impact your intended behavior, right? And this is where new tools are required, new integrations, new standards, et cetera. Historically, if I think about it as an example, our first entry into the 3D IC market was with our Calibre 3D stack tool. As you would expect, coming out of the Calibre space, with our expertise in the sign-off verification stages, that's what we focused on first. And the first thing we came up against was, okay, I've got multiple chips, they're different processes, maybe from completely different foundries, also interacting with all of these other components that maybe we haven't had to consider in the past. How do we understand all of this, right? If we think about like traditional GDS2 for an individual chiplet, we understand things to be based on the layer mapping statements, right? We know that, a metal 3 is on a certain layer. And so anytime I see that layer, I can make certain assumptions about where it is physically within the system and how it's connected. But when we have these heterogeneous systems, you have kind of extra risk that comes in there because one foundry might use the same layer mapping for a different layer, right? And so how do I make sure I'm not confusing those in three-dimensional space? So we built an approach to address this, right, that really allows us to understand where every chiplet is, what geometries belong to that chiplet and are independent of other elements within the whole system, and also, more importantly, understand which ones interface and connect across to other chiplets or other components as needed, so that we can look at it sort of in two dimensions at the same time, right? Understanding the specifics of the chip without losing where it plays in the greater context. We took this capability, we later expanded on it to basically leverage everything we do in the Calibre space in order for us to understand those mappings, right? So it doesn't just apply now to, DRC and LVS, but expands to allowing us to do PERC analysis, to do thermal analysis, stress analysis, the whole 9 yards. Once you have that map, you can bring it with you wherever you go with that specific design. TSMC later expanded on this, as Heather referenced, the 3D blocks offering that they had, which is now becoming an IEEE standard. They took it, they expanded on it, right? Not just to have a map, but then to say, here's all the PDK elements that you need in order to run whatever type of flow you're trying to run. So it makes it really pretty impactful, pretty helpful. It just kind of shows the evolution of this kind of design chain process. How do we pull it all together? In the early days, it was really difficult.
Yeah.
People thinking, do I need to run multiple LVSs across every interface? How do I know which one's which? How do I stitch them together? How do I trace through when I need to? Fortunately, all of that is now gone, right? All of that is removed by some of these integrations and these standards that have been built. So it does show that we're making good progress, but it is a lot of extra work versus the traditional 2D space for sure.
Yeah, I feel like the entire designer community breathes a great sigh of relief every time the IEEE actually announces a standard.
Yes, for sure.
Heather, do you have anything to add to that?
I think from the multiphysics side, we're learning, as I mentioned, that the chiplet or die designer is going to be a part of that conversation and will need to understand in the context of their GDS design plan or execution that what they're planning and executing on is still in alignment with a 3D IC multiphysics standard. And being able to simulate at the die level is going to give them more detailed, accurate information about how to create a reliable, well-functioning product. So without that GDS detail, you're going to lose accuracy and you may miss some of these failure modes that we're seeing crop up with the complexity of the design. The other thing I'm thinking about here is these die level results that also are part of the larger picture. So as we talked about tightly integrating and communicating across these teams, understanding these die level results can be propagated into the next stage of simulation out to down to the substrate or even out to the board level of scale. And essentially what we're doing by adding the capability at the die and chiplet level is enabling a somewhat full digital twin simulation for the multiphysics domain.
So I want to end with one of my favorite questions to ask our guests. I'm going to ask you to gaze into the future moving forward. Where do we go from here ultimately, and what are some of the steps to get there?
Oh, this is something we think about quite a bit.
Yeah.
So from the EDA perspective, we see the clear need for these tightly integrated flows that enable our customers, enable designers to efficiently determine quickly how well their designs will function in the context of all the other 3D IC components. This is, as John was mentioning, a more and more complex proposal, and trying to streamline everything is really where the A in EDA comes from. We're automating as much as possible. We see that the other side of that is going to be automating what a clear criteria for success or failure is. So we like to think of things in terms of sign-off, right? What is the sign-off criteria so that we can proceed with the design and move on to the next phase? When thinking of sign-off from a multiphysics perspective, we're going to need to lean on the mechanical, the thermal, the power experts, timing experts to to really distill down what determines success or failure from a design perspective. I think on top of that, we're working on how do we implement AI in this space. The learning curve is steep. We are looking at folks who have been traditionally designing in the SoC space, moving into a much more complex arena. As such, kind of trying to reduce the slope of that curve, we can start even just with some agentic additions. So we have our Fuse platform, and we're working with users to help them come up to speed faster within the tools. So agentic is a primary space that we are already playing in. And then we are also investing some time and resources into understanding how can machine learning methods create opportunities here, not only to make the flows more usable, but also to make them perform better. So we can reduce this potentially 3-year design cycle timing and have these teams become more efficient, not only in coming into a clean design faster, but also for their use of those tools to be efficient.
As I think about particularly the power to thermal problem, right? There are interesting things that people are looking at, including things like, for one, more photonics and potentially including photonics closer to the chips to help bring signals in a faster way and in a way that does not generate as much heat. Also looking at new materials, maybe glass, maybe ceramics, as ways to kind of create like thermal buffer, if you will, between chiplets. Also, even discussions about liquid cooling at the chip level itself. So a lot of potential exciting things that I think can really help us. This whole power that we're trying to drive through the industries today and how much power we're taking is really massive. The more we can do to bring that down, the better. And also the less heat we're going to generate in the process was also better for us in the long run.
Absolutely. Talking about exciting things, not just in performance, but in efficiency as well. Mm-hmm. Well, thank you both so much for joining us, John and Shweta. We deeply appreciate you sharing your perspectives on this and giving our listeners a little bit of a glimpse into what you see as coming next.
Thank you. It was a pleasure.
Thanks for having us.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again to our guests. EE Times Current is available through the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript along with direct links to the other stories we've mentioned and other resources. EE Times Current is produced by EE Times. It was engineered by Taylor Marvin at Coop Studios. I'm Eric Singer. Thanks for listening.